Rightio, let's get looking at our electrophilic substitution reactions. So far we have looked at our nucleophilic substitution reactions for alkanes. We have looked at our electrophilic addition reactions, so the addition across a double bond. Now we're going to look at our electrophilic substitution reactions. So these ones, just like the electrophilic addition, are going to require an electrophile, so an electron-loving substance that is electron deficient. So let's get started. Primarily what we're going to concentrate on for our electrophilic substitution is the electrophilic substitution of benzene. We know from our discussions of benzene already that it is highly unsaturated but doesn't react like an alkene because of its 1.5 bond order and the delocalization of the electrons in the pi cloud around the ring. This highly stable structure means it's more likely to undergo substitution reactions than addition, because it doesn't want to lose the aromaticity or the delocalization of those pi electrons. So the ring is considered a region of high electron density, so as you can imagine, is very attractive to electrophiles. These delocalized pi electrons seek out electron deficient species, forming a new bond and losing a hydrogen atom, substituting with a new substituent. This process is what we refer to as electrophilic substitution. So the benzene is going to swap a hydrogen for another group. The electrophilic substitution of benzene is another mechanism that you have to know, simply for benzene though. So let's go through the process. The electron pair of benzene is attracted to the electrophile. So our curly arrow notation is going to go from our resonance structure ring within benzene out to the positive or delta positive charged electrophile. This is going to disrupt the delocalized pi system, so we're going to lose aromaticity, and we show this by the dashed ring inside the hexagon of benzene and putting a positive in the side of it. This is a carbocation, as we saw with the electrophilic addition, but that is delocalized within the ring structure. Okay, so we lose our conjugated double bonds, forming the benzene carbocation. Okay, the hydrogen then donates its electrons back into the benzene ring, forming the aromaticity again once the electrophile has attached. So you'll see here that we have both the hydrogen and the electrophile attached. The hydrogen then donates its electrons from that bonding pair back into the ring to make it conjugated pi system again. The electrophile stays on and we're left with H+. So we lose H+ from the ring, okay, to reform the neutral substitution product, okay, regenerating the aromatic ring. So electrons from the ring to the electrophile, leaving us with the hydrogen at that carbon and the electrophile attached and the breaking of the double bond. So we're not breaking any bonding rules here because we don't have the double bond. The carbon now has 4 bonds to it instead of a double and 2 singles. We form the carbocation intermediate, which is the non-aromatic, and then we have a fast step where we lose H+ because the electrons are donated back into the ring. The first step has a really high activation energy. Breaking the aromaticity of benzene is hard because it's so stable. So the first step to form the carbocation has a high activation energy, so that's going to be our slow step. But the final product is more stable once we regenerate the aromatic compound, so will happen quickly. So again, we see this two-humped energy profile where we have the intermediate, which is a little bit lower energy than the activation energy to start with once we form this intermediate, then a lower activation energy in the fast step to get us to the final product. One of the examples that we need to know for this, okay, so other than the generic electrophilic substitution of benzene, is the nitration of benzene. This is adding a nitro functional group, NO2, to the aromatic ring, giving us C6H5NO2. This is done with a special nitrating mixture. You do need to know the formation of the nitrating mixture, okay? And it is a mixture of nitric acid and sulfuric acid, which forms two ions, the nitronium ion and the HSO4 minus ion. The nitronium, the NO2 minus, is going to be our electrophile for the addition. But in order to make this, it's a two-step process from the mixing of nitric acid and sulfuric acid. First, we form H2NO3 plus and HSO4 minus. Then the H2NO3 forms NO2 plus and H2O. These are two equations that you should know for the generation of the nitration mixture. We use concentrated nitric and sulfuric acids, and we heat them at 50 degrees C. Sulfuric acid is the stronger acid, and it protonates the nitric acid, accepting the nitric is going to accept the proton from the sulfuric, and then we'll lose a water molecule in the process to form the NO2 plus electrophile. The NO2 plus electrophile then undergoes the exact same mechanism we were just talking about. The arrow goes from the aromatic ring into the NO2 plus electrophile. The positive is transferred to the carbocation, and we have the hydrogen and the NO2 group both attached to the non-aromatic benzene ring. In the final step, we lose H plus and form the NO2 substituted benzene. So when we write the overall reactions using the conditions, we have benzene plus nitric acid in the presence of concentrated H2SO4 at 50 degrees C, gives the nitrobenzene and water. Okay, in this case, you can see that the sulfuric acid is acting as a catalyst because it will be regenerated at the end of the reaction, because the HSO4 minus ion will pick up the H plus that is generated, reforming the H2SO4. That's it. That's the only reaction that you need to know for the electrophilic substitution. It's benzene and the nitration. We'll talk a little bit later when we talk about the reduction of the nitro into the amine. But for the electrophilic substitution, it is electrophilic substitution of benzene, and we need to make sure that we know the conditions for the nitration process. And I'll see you in class.